was saying, when you have a linear restriction imposed on one or more coefficients of your multivariable regression model, you can decide or test the hypothesis whether the restrictions are satisfied based on the F test. And this F test, when you apply it for such a situation, is called the restricted least squares test. The basic procedure is you first run the unrestricted model and then you impose the restriction and modify the original model so that you get a restricted least squares model. On running this restricted least squares model, you will get the associated R square, or from which the residual sum of squares can be calculated. So based on that, you can use this formula to calculate an F statistic, which is residual sum of squares of the restricted model minus residual sum of squares of the unrestricted model divided by M, where M is the number of linear restrictions imposed on the original model. And in your denominator, you will have the residual sum of squares of the unrestricted or the original model divided by n minus k, which is n is the number of observations and k is the total number of parameters that have been estimated in the original model. Now this will obviously follow the F distribution with degrees of freedom m and n minus k. Remember, m is the degrees of freedom of the numerator, n minus k is the degrees of freedom of the denominator. As usual, find the critical value at whatever your alpha level of significance is, 5%, 1% or 10% or any other value. And if your calculated F statistic is greater than your critical value, it will fall in the rejection region and you will reject the null hypothesis of the linear restriction. On the other hand, if your F statistic is significant, it does not fall in the rejection region or the critical region, that means your F statistic is insignificant. That would mean that your null hypothesis is accepted or that the linear restriction is satisfied in this model. Now, one more bit, if you remember, I had uploaded a very short 3 or 4 minute video about relationship between F and R square, right? Our coefficient of determination R square. Now, similar to that, we can also use the R square value over here. The formula then becomes F is equal to, in the numerator, you will have R square of the unrestricted model minus R square of the restricted model. Degrees of freedom remains the same. So divided by M, which is the number of linear restrictions imposed on the model. And here you will have 1 minus R square of the unrestricted model in the denominator divided by n minus k. Right? So this formula is very useful because especially when because R square is reported in almost every statistical package for every regression that is run. So no more calculations are required, simply use the R square. But point to keep in mind, nota bene, point to keep in mind, when you're using this formula, R square of the unrestricted model and R square of the restricted model should have the same dependent variable. That is, if it is ln y in the unrestricted model, even in the restricted model, it should be ln yi. Right? So just remember that only if this particular, if the same dependent variable as is satisfied, only then can these two values be directly comparable. Okay, only then can these two values be comparable. If your dependent variables are different, you cannot use R square of both the regressions and calculate the F statistic. It will give misleading results. Okay. Now, from the book, I have taken a photo of the pages in the book that I have here. Here, you can also follow your own Gujarati book. I think the soft copy that has been uploaded may not have this output. It might have something different because that is the fifth, that is a different edition, and this is an Indian edition. Okay, so I wasn't sure, that's why I have put a snapshot. What I want you to do is I just want you to look at the output table here, right? So first we have the original regression. So it is ln yi, or the log of output, and your x variables are log of capital and log of labor, right? Log of capital and log of labor. So the t values are shown, the p values for each of these coefficients are also shown. So based on the p values, you can see that the coefficient of capital is very, very significant. Even at 5% level of significance, the coefficient of log labor is quite significant, and so on. The intercept, on the other hand, if you see, 0.054 is the p-value, which is greater than your, if you assume alpha to be 0.05, it is greater than 0.05. So not significant at 5% level, but it is significant at the 10% level of significance, right? So this is my R square, 0.979, very high R square, that's very good. And the residual sum of squares of this unrestricted model, this is the unrestricted model. That's why the subscript UR has been given. It is given to us as 3.967. Okay. Now, if you add up beta 2 and beta 3 here, it is 0.799 plus, let me just erase a few unwanted lines, okay? Okay. If you add up beta 2, which is 0.799, and 0.254, beta 2 plus beta 3, for this sample, we get the value as 0.799 plus 0.254 comes out to be 1.053. So here, my sample beta 2 hat plus sample beta 3 hat value comes up to be 1.053. Yeah, I've added up 0.254 and 0.799. So based on the sample value alone, since beta 2 plus beta 3 is greater than 1, we would tend to say that probably the Indian economy has increasing returns to scale. Okay, this is the Cobb-Douglas production function, which was attempted for the Indian manufacturing sector 2008-9 data. So based on this sample, I can see that beta 2 hat plus beta 3 hat is greater than 1. But now I want to find out if this 1.053 is statistically greater than 1. If it is, then I can say that Indian manufacturing sector exhibits increasing returns to scale at this moment. And if it isn't, then we will have to say that we have constant returns to scale being exhibited in the Indian manufacturing sector. Okay, so I impose the restriction beta 2 plus beta 3 is equal to 1. I build it into the model, and as I showed you earlier, once that restriction has been built into the model, I can change the dependent variable to log of output per unit of labor, yi by x2i, right? And my x variable or my independent variable or the explanatory variable has been transformed to log of the capital to labor ratio, right? So now we run this new model. This is actually our restricted least squares model, and as you can see, because one restriction has been imposed, I now have only one parameter less to be estimated, only beta naught or the intercept, and beta 3 is being estimated. Right now, if you see the p values of both these coefficients, both are very small, which means they are quite significant. Okay, the r square, this is the r square of the restricted model, is 0.774. Now you should never be surprised, always r square of the unrestricted model will be greater than or equal to r square of the restricted model. Never be surprised, because see, once your restrictions are imposed, your number of parameters to be estimated will reduce, right? That means your number of explanatory variables will also reduce, and you know that the value of r square is directly proportional to the number of explanatory variables. Here, since the explanatory variables and the number of parameters to be estimated has reduced, my r square is also likely to reduce. And this model gives me the residual sum of squares of this restricted model. The subscript r means it's the restricted model. It is 4.355. Okay. Now, the unrestricted model, the dependent variable was ln y, or log of output. In my restricted model, my dependent variable is log of output per unit of labor. Since the dependent variables are not the same, remember, I can only use this particular formula in terms of the RSS, or the residual sum of squares. So I'm calculating the F statistic. This is the formula that I wrote in the earlier slides. The values of residual sum of squares of the restricted model, 4.355, I showed you in the last slide. 3.967 is on the last, two slides back. M is 1 because only one linear restriction has been imposed, which was that beta 2 plus beta 3 is equal to 1, or in other words, I'm saying beta 3 is equal to 1 minus beta 2. One and the same, whichever way you put it. So one restriction has been imposed, so M is 1. N minus K, okay, the details of the sample is not visible in this picture. Basically, my total number of observations was 31. Okay. And K, that is the number of parameters that was estimated in the unrestricted model, was the intercept, the coefficient of associated with log of capital, and the coefficient associated with log of labor. So 3, right? So N minus K will come up to 28. That's how we got this. Now the value of F statistic calculated is 2.74. Now in the using the F tables at the back of any statistical and log book, you can check for the F value at say 5% level of significance, degrees of freedom 1, 28. And you can see that at the 5% level of significance. So now you have to check the F statistic value, F equals to 2.74. Is it equal to, or compare it with the critical value of F distribution with 1, 28, right? So to do that, I have just taken a photo of the F table. This is from again Gujarati's appendix D, which has all the statistical tables. Okay, so just to show you how I look at it, if you can see, on top is the degrees of freedom of the numerator, and here is the degrees of freedom of the denominator. Now numerator, my degree of freedom was 1, denominator, my degree of freedom was 28. Okay, so the value that I'm going to look at, and okay, I'm assuming alpha is equal to 5%, which is 0.05, right? So probability, degree of freedom, numerator 1 and denominator 28. This is the section that I'm interested. And what is my probability alpha? 0.05. So 4.20 is the critical value. My critical value is 4.20. And what was my F statistic that I had calculated? 2.74. Since 2.74 is less than the critical value 4.20, I am forced to accept H naught. What was it? That beta 2 plus beta 3 is equal to 1. Which means, although in this sample I am saying that beta 2 plus beta 3 is equal to 1.053 or greater than 1, statistically it is not much different from 1, and that means that the Indian manufacturing sector is following or does exhibit constant returns to scale. So my restricted model is correct. Okay, so if I'm saying it exhibits constant returns to scale, I can always work with the second restricted model as the correct model for this analyzing the data of the Indian manufacturing sector. So I hope this one example of how we look up the critical value is clear. If you have any doubts, please feel free to ask me. I can give you more clarifications. Okay, any doubt over here? This table is there at the back of your Gujarati books. It is there at the back of Clark's tables. All standard logarithmic and statistical tables book have these F distribution critical value data. Okay, so this is how we did the restricted least squares hypothesis testing. Thank you.